To solve this problem, we need to start with the mass of titanium tetrachloride. So I'm going to start with 263.1 grams, TiCl4. Now, 99% of the time when you see grams in this class, you really should be converting it to moles. So how many grams per mole of titanium chloride are there? Well, we need to look at the periodic table and find the molar mass. And I find the molar mass is 189.9 grams, TiCl4. So now I have moles of titanium chloride. Now, how much energy is required to melt this many moles of titanium chloride? Well, now I need to look at the delta H of fusion. So the delta H of fusion is the energy required to go between the solid and the liquid. When we're talking about melting, we're talking about going from solid to liquid. So I'm going to use this energy as a conversion factor, and I'm going to convert moles of titanium tetrachloride into kilojoules of energy. So the 9.37 stays with kilojoules, and that is read as kilojoules per 1 mole. Now let's just double check our stoichiometry here. We have grams titanium tetrachloride cancel with grams. Moles cancel with moles, and we are left with kilojoules. So when I run this in my calculator, I actually get 12.98 kilojoules. Now I'm just going to double check my significant figures. I had 4 sig figs here, but 3 sig figs here. So I'm actually going to report 3 significant figures, and I would report 13.0 kilojoules of energy is required to melt that much titanium tetrachloride. So for B, which will likely have the larger magnitude, the delta H of fusion or the delta H of vaporization? And explain. Well, the delta H of fusion is the energy required to go from solid to liquid. Like, I can spell liquid? Sure. And the delta H of vaporization is going from liquid to gas. So now we have to understand the interactions between our phases of matter. In a solid, that's where our intermolecular forces are exerting the most effect. So we're really holding on tight with a solid. With a liquid, we're kind of in that middle range because they pass along like we're in a crowded room and holding hands with one person at all times. But when you're a gas, you're as far away from one another as possible. So you're going from interacting to no interacting. So we're breaking, but we aren't remaking. Okay, that's how we can look at those interactions. From a solid to a liquid, we're breaking some of the interactions between a solid and a liquid because we're always going to be holding hands with something. So the H of vaporization should have the larger magnitude because we need to break all of those interactions and not have any more interactions left. So it should take a little more energy to do that. That would be the explanation for that. Hope that helps.